Hello and welcome to the course Design Board Fields with Confidence. This is the second chapter of this seventh part, and we will be taking a look at our first method that is typically used when we're designing geothermal bore fields, namely calculate the required borehole depth. Now, this methodology, although a little bit self-explanatory, basically assumes you start with a given configuration. For example, you say, well, we're going to drill 4 boreholes, but you want to know how deep they should be in order to make sure that your entire building demand is fulfilled with the geothermal system while staying within your temperature limits. And conceptually, that looks a little bit like this. So what happens is we start with a certain initial guess. In GHEtool it's 100 meters deep in the backend. And what we do is we calculate the temperature profile. We see, well, do we stay within the limits or do we cross it? And then we cross the temperature limits, the depth is increased. We recalculate the temperature profile, and this we iterate until we converge and make sure that we stay within the temperature limits and that your borefield is sized accurately. So that is conceptually how the algorithm works. But before we look at some examples in GHEtool, let us talk about the different ways you can do this basically. Because in literature there are 5 different levels of sizing accuracy for geothermal bore fields. Starting with the L0 method, which are rule of thumb ways to cope with this problem, all the way up to sizing with hourly resolution. Now, let us go over them in a little bit of detail. When we're thinking about a level 0 sizing, it's basically always in the form of 30 watts per meter, 40 watt per meter. It's basically a way of saying your total borehole length is directly proportional to the peak power of your system. But this, of course, does not consider the configuration. Are your boreholes on a line? Are they in a grid? Are they scattered around? You do not have any information about this. You're also not calculating the actual depth. It's just saying, well, we need this amount of meters, but how deep it is, you don't know. It does not consider any imbalance. It does not consider the borehole thermal resistance. So basically it should be avoided when working with bore field sizing due to the very high inaccuracy. And basically we also covered this back in the first chapter when we were talking about, well, why should you follow this course? Why is bore field sizing important? When we go to the first level, basically what we're doing there is we will assume a constant load. So this already takes into account the bore field configuration, the borehole depth, the imbalance, the borehole thermal resistance. So we already have some information, but assuming your entire building load is a constant, well, it ignores basically the first year, it ignores monthly variation, it ignores variation in peak power. So it's not really accurate, but at least we already have some information about the bore field itself instead of just relying on a linear proportional relationship. Now, just looking at an example how this would basically look like, it's like this. So we clearly see here our G function coming back in the borehole wall temperature, and our fluid temperature is a constant temperature separated from this borehole wall temperature due to the effective borehole thermal resistance. But as you can see, yeah, you already see some long-term effect here, but it's clearly not an accurate way of sizing your bore field. When we're going up from level 2 to 4, basically we're actually sizing some. And what this sizing means is we will first always size our bore fields for the maximum temperature limit, and we will also size it for the minimum temperature limit. And then in the end, our final size, it will be the maximum of this first and this second temperature. Because, as we discussed also in previous chapters and parts, a bore field can be either limited by the maximum temperature limit or by the minimum. So it's important that we check both in order to make sure that our final size is actually working with both the maximum and the minimum limits. And the first sizing level or level of accuracy that does that is the second level. And this is also called the ASHRAE sizing equation. It's a really common way of designing bore fields, and it basically uses 3 pulses for every simulation, every calculation of the required depth. Now the one pulse that considers the imbalance, and it takes into account the long-term effect of, or the long-term temperature drift due to the imbalance. The second one is the monthly pulse, so it's going to look at which month is the worst case, where is the extraction or injection load the highest, and then it will also consider the peak power in that month. And with these 3 pulses, we can consider the configuration, the borehole depth, the imbalance, the borehole resistance, both for heating and cooling. But again, this method ignores a monthly variation. It's a very simplified approach. Besides things, it's also not implemented in GHEtool as such. And it would look something like this. So you have the same graph as with the level 1, basically, so the long-term effect. And then we see a sudden jump in temperature, and that's because we have, you see the black line going down. That's because we have the monthly load in this last year, and then we also have the peak power in that case. So you also see here, well, we have some long-term effect, we have some short-term effect, but it's not really sizing anything. And the first level that actually is familiar to you, let's say, it's the level 3. It's the most accurate method when there's only limited information available. It's to say, we are sizing now with monthly time steps. So instead of working with 3 pulses over the whole simulation period, we're now working with 12 pulses per year in both heating and cooling, so actually 24. And this method is implemented in GHEtool Cloud, and what is interesting is that we again consider configuration, borehole depth, imbalance, borehole resistance, now changing at every month in heating and cooling, due to the fact that we use variable flow rate, variable fluid properties. We discussed that already a couple of times in the previous parts. But now we also can consider the monthly variation. There is a monthly profile behind it. The only downside of this method is that we still assume a peak duration. And we already covered this, but the peak duration, it's a mathematical trick to basically overcome the fact that we do not have any hourly data. We do not know how long the peak duration is, so we have to assume a peak duration a priori. And this level 3, it looks like this. You're very familiar with it. It's basically the way we have been designing bore fields throughout this course, and we will do in the chapters and parts to come. And the last level, which is the most accurate one, let's say, it uses hourly time steps. So we do not need an assumption for the peak duration anymore because it's embedded in the profile. We know at every hour what the borehole wall temperature is, what the fluid temperature is, what the borehole resistance is. So it's a really, really accurate way of designing also when we will be looking at, for example, things like simultaneity in the next part. The only downside of this method, and now we're getting a little bit technical, is that we do not yet consider the borehole dynamics. It is to say, working with the effective borehole thermal resistance, it's a steady state approach, and we already covered that. But in fact, there is also some transient effects. And when you extract heat from the borehole, it's first coming from the fluids, and then from the grout, and then from actually your geothermal bore field itself. And this thermal inertia is not yet taken into account, but we are constantly working with universities to also make this more accurate. So that's something to come. And the level 4 sizing, it looks then something like this. You can zoom in on it if you really want to see the hourly variation, but basically there is now an hourly variation in your sizing. So these were the 4 levels, 5 if you include the rule of thumb, of different ways to design your bore fields. Now, before we jump into an example, I want to talk with you about the unsolvable due to gradient error. Because when we're designing with this methodology, sometimes there is no feasible solution. And in order to understand that, we need to consider, or we need to remember, that GHEtool considers both the maximum and the minimum temperature limits, in contrast to other design software. So consider the case where there is a constant ground temperature. So you go to GHEtool, you say it's a constant temperature, and this means that no matter the depth, the ground temperature is constant. And if we're in this iteration loop, we're guessing we start with 100 meters, we say, okay, our fluid temperature is above the threshold, the algorithm will increase the borehole depth, and this also increases the total borehole length, which means that we will have less injection power per meter borehole, which also means that our fluid temperature, our maximum fluid temperature, will be lower. And if we keep iterating like that, we will end up with a borehole depth where actually our fluid temperature is below the threshold and we have a solution. However, most common, it's the situation where you actually design with a ground temperature gradient, meaning that if you go deeper, your ground temperature becomes warmer. And when that's the case, and your fluid temperature is again above the threshold, and the algorithm will say, okay, let's drill deeper, you have more borehole length, you have less power per meter, your fluid temperature will be lower due to that. But on the other hand, you now have also a higher average ground temperature. Because you drill deeper, the ground becomes warmer, and yeah, this shifts basically all your lines up, increasing your maximum average fluid temperature. So basically, when you're limited by your maximum fluid temperature, the solution, or what the algorithm basically wants, is having more boreholes instead than deeper ones. And to illustrate that, let's us consider the following graphs. So here, the case with a constant ground temperature, you see the ground is, no matter the borehole depth, it's constant, at 10.5 degrees if I'm not mistaken. And you see that your fluid temperature, it drops off when you're increasing the borehole depth. And this is because when you're drilling deeper, we have less power per meter borehole, lowering of fluid temperature, bringing your fluid temperature closer to the ground temperature. Now, you see here a certain difference. That's a technicality due to the way the borehole resistance is calculated. It's over in the textbook if you want to have more details about that. But basically, the deeper you drill, the closer your fluid temperature comes to the ground temperature. When you're working with a ground temperature gradient, you again see this orange line going down because we're drilling deeper. But now you also see your ground temperature increasing with the borehole depth. And then this green line is actually the combination of both effects. So both our ground temperature becomes warmer if you drill deeper, but also your fluid temperature becomes closer to the ground temperature. And this creates this, it's not a parabolic, but basically a downward going slope. And then after a certain depth, it increases again. And if you look at this more conceptually, if this curve, this downward and then upward going curve, is above our temperature threshold, there is no depth in which our fluid temperature is below the threshold. And then we create this unsolvable due to gradient error. And the only way to overcome this is by saying, well, instead of having, for example, these 2 boreholes, let's drill 3. This will shift the whole curve down, and now we will end up with some depths that are below the temperature threshold, so depths where our fluid temperatures will be below our maximum limits. And in fact, there are 2 solutions often, one with a shallower depth and one with a deeper depth. And without going too much in detail, you know that this algorithm is iteratively, and we discussed it in the beginning of this video. So basically what happens traditionally is we start with a guess, we calculate the temperature, we make new guess, and we do this until we converge to either one of 2. And since this is mathematically possible to see, well, which solution you converge to, we have developed a new algorithm for this in GHEtool that's called deep sizing. And basically what we do here is we start by having a small borehole depth, and we go straight down to having the solution where the borehole meters are actually the smallest. So this is a little bit of theoretical background on how this method works, what the gradient error is. Now let us jump into GHEtool, see when the gradient error pops up, how you can overcome this, and how you can use this methodology to calculate the required borehole depth. So here we are in GHEtool Cloud. I created a new project for you, and we are going to work with the calculate required depth method. Now again, if you want to follow along, the full report with all the assumptions and all the input parameters is in the download section of the corresponding chapter on the website. We will be working with 0 and 17 with the average fluid temperature. Now there are some questions on how the results would change if we go from inlet to outlet temperature. Please go ahead and try it for yourself to really understand the importance of what we discussed in the last chapter. For the ground properties, let's work with the standard values, ground temperature gradient. We will work with 4 boreholes in this case, just on a line. The borehole resistance will be a W with monopropylene glycol, and we will be working with a constant temperature difference for our flow rate, meaning that our flow rate will be updated in every month during heating and cooling separately, as we discussed a couple of chapters and parts ago. And for the thermal demand, basically the default value is 15 kilowatts heating, 10 kilowatts cooling, and 22 megawatt hours per year in heating and 7.6 megawatt hours in cooling. Now let's give this to the server and let it calculate it for us. And as you can see, we end up with this gradient error. And there is no solution possible because we are probably limited by the maximum fluid temperature. So let us go ahead and duplicate this, call the scenario 2, 5 boreholes. Let's go back to the bore field. Let's say, okay, instead of having 4, let's do 5. Calculate it again, and now see if the algorithm gives us back a solution. So if we go to the results, we see indeed here we now have a solution. We need 5 boreholes of 160 meters deep, and yeah, indeed you can see we were limited by this maximum limit. We're nowhere close to our 0 degrees Celsius. So in this case, we couldn't find a solution with 4 boreholes because, yeah, the algorithm would go deeper than 116 to 130, 40, 50, and so forth. And yeah, there was no feasible solution. When we have 5 boreholes, there actually was one. Now, another way of overcoming this, because this was by adding other boreholes, we can also say, well, this was now with passive cooling, and we were in the range of 0 and 17 degrees, 17 degrees being typically a temperature when you're working with passive cooling. We can also say, let's go for active cooling. Now here we can simply say the efficiency goes down because now our compressor also has to work. And our general tap, we can, for example, increase the fluid temperature to 25 degrees. Now, before we see the results, I want to draw your attention to this warning here below. And that's because if you're sizing, let's go back, calculating the required borehole depth, what the algorithm does is it iterates the depth indeed, but if you have a heterogeneous ground with different ground layers, it can be that the depth of 100 meter has a different ground conductivity than at 150 meter, for example. And that's why it's suggested here that if you use this methodology, that you actually enter your ground with different layers, because then you will have a more accurate result. Now in our case, it was sand all the way through, so our conductivity was fine. But if you have a heterogeneous ground with some rock, with some clay, with some sand, it could be valuable to enter it in layers. Now let us go back to our results. And here we can clearly see now we're limited by the minimum average fluid temperature. Our maximum is no problem whatsoever. And now we can also cope with these 4 boreholes. But what you can see here, the 4 boreholes of almost 92 meters drilling depth, we are above the 0 degree, but yeah, we cross our 17 degrees. So indeed, there was no solution possible with passive cooling. And actually, that's typically the case when you're working with this calculate required depth option. And that since we also consider the maximum limit, you often run into this gradient error, and you either have to switch to active cooling or add a number of boreholes in order to make sure that your bore field is big enough to cope also with this maximum limit. And that's why in the next chapter we will not be looking at the method to calculate the required depth, But we will be discussing a method that can automatically calculate the required size, the required number of boreholes, together with your depth, in order to overcome this gradient error and save you some time with doing trial and error. So let's talk about that in the next chapter.